So I recently watched this video by Mr. Zozin called One Formula That Demystifies 3D Graphics. And I thought it was really interesting. It was a great introduction to 3D to 2D projection. And I wanted to take it a step further. So let me just show you the intro to the video first.
It goes like this. Imagine that you have a 3D point in an imaginary 3D space behind your screen. And to project that 3D point onto your screen, what you have to do, you have to take its x divided by z and its y divided by z. And what you will get is the point on your screen projected. And if you just have a bunch of points behind your screen in that 3D space and you start animating them and rotating them, and then use this formula to render all of these points on your screen, all of that will feel like a 3D scene,
Okay, so basically using this simple formula that apparently he's been thinking about since high school, he creates this using just HTML5 canvas, using a 2D context and just rendering lines. And at the end, so he has this spinning cube, and then he just pastes in the vertices and faces of some Penga model. But he didn't actually show how he went from the Penga OBJ file to actually putting it in the format that he needs. So that's what I wanted to do today, is actually build a OBJ importer, so that you can import any arbitrary OBJ file and render the wireframe in a HTML5 canvas. So let me just show you his final result.
and roughly 626 faces. If we copy paste this entire model instead of our cube, we get something like this. And please notice that we're not using OpenGL, WebGL, WebGPU, or anything like that. The only thing we use is 2D HTML context and a very simple formula that I kept thinking about to this day. So yeah, have fun with this formula.
Have fun, we will. So basically, I have that working. I didn't copy it line for line, but after watching the video, I implemented it myself and went back a couple of times when I got stuck. And so we have the cube rendering and spinning around. And now we want to basically add a file picker so that we can add any OBJ file we want. So this is basically very similar to what he did. One thing I changed is that I made the canvas size, basically it fits the viewport. So it also compensates for the aspect ratio, so the cube always remains a cube. So if we look at my code over here, it's, the whole thing is less than 100 lines. And basically over here, we have what I just talked about, where the canvas is being set to the window inner width and inner height, minus 20 pixels. And the aspect ratio is being compensated for in the projection. We're dividing the X by the aspect ratio. So now the reason we want to use OBJ format in particular is because it's the simplest format that there is, basically for 3D models. It's a text-based format and it's very easy to parse. So here is the Penga OBJ file. We can see firstly it linked to some material library, which we don't care about today because we're not using any materials, we're only rendering wireframe. And then every vertex is listed as its X, Y, and Z coordinates. And then we also have the vertex normals, VN, and VT, the vertex texture coordinates. Once again, we don't care about those because we're only interested in the wireframe. And then we have F, this is the faces. So a face can actually be made up of more than 3 coordinates, like in our example, with our cube, we have faces with 4 coordinates. So that's totally fine. But usually in most 3D models, they use triangles because triangles are the most efficient for graphics cards to render. So they're going to be 3 vertices per face. So what we have here, actually, the first number in each set of 3 is the vertex index, and the second number is the index of the vertex texture coordinate, and the third number is the index of the vertex normal. So once again, we don't care about the textures and normals, so we only care about the first number in each set of 3. And these are actually the 1-based indices of the vertices. So, if we have a face that has a vertex 1, for example, this face, that's actually referring to the first vertex that is in this object. So yeah, very simple format to parse, so let's do it. The first thing we need is we need an input for the file, and we'll give it an ID as well, so it's easy to access in the JavaScript, and we can actually restrict it to only accepting OBJ files. So if I refresh here now, here it is, but this has created a scroll bar, so really quickly I'm just going to change the height to be 50. There we go, scroll bar is gone. Okay, so now what we want to do is to write the importing and parsing of the OBJ file. So I'm just going to do file dot lowercase f, add event listener change. We're going to call the function import OBJ. So now we're going to get the first file, because in a file input you could actually add multiple, and we're just going to make sure that there's actually a file defined there. Okay, and now we're going to read the text from the file. So text equals await obj.text, and since we're using await, we also need to make this an async function. And now we're going to get the lines by splitting the text on the new line character. Okay, and now we're going to process the file line by line, and we're going to split each line into parts by splitting it on the space character. Okay, and now we're interested in lines that start with either a V or an F. So if parts 0 equals V, we're going to process a vertex, and if parts 0 equal F, we're going to process a face. But also for vertices, we need to make sure that there are exactly 4 parts, so the V and the 3 values. And then similar for the F, but as we said, it can be any number of vertices greater than or equal to 3, so there must be at least 4 parts to the line. Okay, and now for vertex, very simple, we're just parsing floats for all the different parts. So X is going to be the first part, Y will be the second part, and Z will be the third part. And now we're going to actually need a list to store the new vertices and the new faces. So now we're just going to say new vertices dot push V. And now for the faces, so they're actually arrays, right? So we need an array of all the vertices in that face. So we're going to create an empty array. So let face equals array. And now we're going to do a for loop from I equals 1 until I is less than parts.length. Okay, and so now for each part we're getting the vertex index, right? So we're going to do, in this case, we're parsing an int of parts I, and now we're actually going to subtract 1 from that, because while the OBJ file uses 1-based indexing, we use 0-based indexing in our faces, as we can see here. So we're subtracting 1 from that, and now we're doing face.push vertex index, and finally new faces.push face. Okay, and now we're just going to do a little bit of validation on that. So we're going to check that the new faces, that there is at least one face, and also we want to make sure that there's no vertices being referenced in the faces that don't actually exist, right? So we're also going to, this shouldn't be within the line loop, and we're also going to create max vertex index, and now every time we get a vertex index, we're just going to calculate which one is the maximum, and now we need to ensure that this is less than the length of the new vertices. So if so, we can now set that to faces equals new faces, vertices equals new vertices, and I'm also actually going to reset the Y rotation angle. So this should be working. Let's test it out. And we have our Penga. So he's not perfect, like he could be, centered a bit better and using the space a bit better. And actually, we got kind of lucky with the Penga, because if I choose, for example, I've got the teapot, the scale is totally messed up, right? So there are a few more things that we need to do to make this work properly on any OBJ file. So what we're going to do is compensate for the midpoint and the scale of the vertices. So in order to do that, I'm going to need to keep track of the minimum and the maximum of the X, Y, and Z values. So I'm going to define here min X, which will start off as infinity, min Y, and min Z, and then same thing for the maxes, except they're going to be initialized from negative infinity. Okay, and so now every time that I calculate a vertex, I'm going to say min x equals math.min of v.x and min x. So same thing for y, z, y, z, y, z, and same thing for the maxes, right? So max. Okay. So that's that. And now we're going to use these values to calculate the midpoint. So once we validated that we're going to use these vertices and faces, so we'll say midpoint is going to be, so it's going to be the min x plus the max x divided by 2. So same for our y and z. Okay. And now what we're going to do is also calculate the scale. So the scale, what I'm interested in is actually the maximum difference between the maximum and minimum value in the three vertices. So we're going to do max x minus min x, max y minus min y, and max z minus min z. And that's because we want to know basically the largest difference between the maximum and minimum in any axis, because we want to make sure that we can scale it properly to fit on our canvas, right? So now the vertices, I'm actually going to map them, and what I'm going to do is map them by moving them firstly to be centered around the midpoint. Okay. Yeah, same thing here for y and Z, centering them all around the midpoint. And then what we also need to do is to divide them by the scale, because we want them to be unit scale, right? So this is now setting them all to unit scale, but actually in our case, the little scene we've defined here basically is a scene with a scale of 2, right? So we're rendering everything in a box of from -1 to 1. So actually we want to now multiply the unit scale by 2. Okay, and now our Penga should be looking much better. Let's try it out. And there we go. Now it's perfectly centered and scaled, and now our teapot should look just fine as well. Great. So what I want to do now is there's actually one more issue here that we haven't solved. So I have one more model here, which is a hand, and it's scaled fine, it's in the midpoint fine, but look at this hand in Blender. Do you notice any difference? So what hand is this? This is actually a left hand. But back in our renderer here, this is actually a right hand. So why did it get flipped? So this is actually due to a concept known as chirality, or handedness. So it only matters when you have an object that has no plane of symmetry, right? So both our other objects, the Penga, right, I could cut it down here in the middle and it's exactly the same on both sides. And same for the teapot. If, long ways this way, if I cut it, it's exactly the same on both sides. So it has a plane of symmetry. On the other hand, our hand does not have a plane of symmetry, right? There's no way to cut this hand in two that the two pieces will be exactly the same. So in a 3D coordinate system, it can be defined as either left-handed or right-handed. And the easiest way I found to explain this is if you take, for example, your left hand, and my camera feed is actually flipped, so this is my left hand, and then if you create an L, and then you point your middle finger forward, and now you define an axis to each of the fingers. So you take whichever axis you've defined as up and put that on your middle finger, and now you have to label the other fingers in X, Y, Z order from your thumb to the middle finger, right? So if this is Y, this is going to be X and this is Z. If we've defined up to be X, this will be Y and this will be Z. And if we've defined up to be Z, this will be X and this will be Y. And now the point is that here, if I have a right-handed coordinate system, there's actually no way to rotate my left-handed coordinate system in order to be the same as the right-handed coordinate system. So, for example, if on the right-handed coordinate system I also have Y up, I can rotate it this way in order for X to still be to the right, but in that case Z, instead of being towards the screen, Z will be towards me, right? So just like there's no way to rotate your left hand to make it a right hand, there's also no way to rotate a left-handed coordinate system and turn it into a right-handed coordinate system. So the way we're going to sort this is we're going to add a checkbox that allows the user to actually decide if they want to flip the handedness of the imported object, because some objects will be left-handed, some will be right-handed. We don't really know from the OBJ file which coordinate system it uses, so we're just going to let the user decide if they want to flip the handedness. And now we're going to define a flip handedness boolean, which we're going to default to false. And all we actually have to do is negate the Z axis during the import. So basically, if flip handedness is set to true, we're going to do negative Z, otherwise we're going to keep Z as it is. And now we're just going to write the event handler for the checkbox. So add event listener, change, I'll I'll just write an anonymous function here. So basically, if e.current_target.checked, we're gonna do flip handedness is true. You know what? I'm just gonna make this simpler. e.current_target.checked, and we also want this to actually, if we've already imported it, we want it to go ahead and flip it. So we're gonna say for const v of vertices v.z equals negative v.z. Okay, so that should be everything. And now if I refresh this and I upload the hand again, so we can see that, yeah, as before, this is a right hand incorrectly. But if I check the box, now this has turned into a left hand. Right, and if I have, if I refresh and I have it checked before I import, and again I select the hand, once again it's going to be a left hand, as the same as it is in Blender. So remember, this is a left hand. Now the thing is, this actually makes no difference to the penga. So if I import the penga and I flip the handedness, there's actually no difference to the model, and same thing for the teapot, right? There's absolutely no difference. So yeah, once again, this only matters for models that actually have no plane of symmetry. Only then does handedness become relevant. But now we can basically, if we import models that are made in a right-handed coordinate system, like Blender is by default, and our system here is left-handed, so we can actually display them correctly. So the last thing I wanted to do here is actually add the ability to rotate the object with my mouse. So I'm going to use the on mouse up, mouse down, and mouse move events. So first I'm going to define a few more variables. So let mouse is down equals false, and I'm also going to define last mouse x and last mouse y so that I can calculate their deltas during the mouse move. So now I'm going to add the event listeners. So we're going to do canvas.add event listener, mouse down, and yeah, we'll just do an anonymous function here. So mouse is down is now true, and we're going to set last mouse x set to e.client x, and last mouse y is e.client y. Okay, so now we're going to do mouse move, and basically we're going to actually do this on the document, and also mouse down will also be on the document, so that in case our mouse click goes down somewhere outside the canvas, the mouse is down actually still takes place. So what we're going to do now is just fill out mouse move. So we're going to say dx equals to e.clientx minus last mouse x, and dy equals client y minus last mouse y. Now we're going to do the actual rotation, and then at the end we're going to set these for the next mouse move event. And so an X mouse movement, so going from left to right on the screen, is actually would make sense to do a Y rotation, whereas a Y mouse movement going up and down on the screen, I actually want to make the object lean forward and backwards. And so that would be an X rotation. So what I'm going to do is, now our rotation angle currently is defined as only, and let me actually move these to the top as well. So our rotation angle is defined as just a single angle for Y. So I'm going to change this into an object. I'm going to say rotation angles, and now it's going to be X, Y, and Z all set to 0. And now wherever I have Y rotation, I'm going to change that to rotation angles dot Y for now. But also, so I'm going to need a rotate function for X, and even though we're not going to be rotating Z right now, we may as well create a Z rotation function as well. The way the rotation function works, you can look it up if you want to understand the maths behind it, but just in terms of how to turn the rotate Y into the others, basically the axis that's being rotated around, that one is not being moved. So here in the original one, we're rotating Y. Y is being unchanged. So when we rotate X, X will be unchanged. And then Y will be, so each one is itself times cosine. And then plus or minus the other one that we are using, in this case Z, times sine. And so the first one after the one you're rotating around, so we're rotating around X, so we're going to say the first axis is Y and the second is Z. The first one gets the minus. So this one will have minus Z times S, and this one will be positive, and this becomes a Y, right? And similar story here. So we're rotating around Z, so Z remains just as Z, and then Y becomes Y times C, and then plus or minus, in this case, because we're rotating around Z, the first one is X, so X becomes the minus, and Y is going to be plus X times S, and this one changes to Y. So that's just an easy way to remember how to do them, but if you want to understand the maths, you'll have to watch another video for that. So now I have the 3 rotation functions, but I need a function to rotate all 3 at once. So I'm just going to call this rotate and X, Y, Z, and now I'm going to call this angles, just so that it's clear that this is now an object of X, Y, and Z angles. And so basically what I'm going to do now is call all 3. And now the order is actually important. It's not the same doing the X rotation and then the Y, and doing the Y rotation and then the X. If we look at our Penga here in Blender, and I've aligned it so that Y is up just like in our coordinate system, and it's currently set to rotate X then Y. So if I rotate X then Y, and that means, if I set X to something like whatever, 82, it's leaning forward just as I'm going to expect. But now if I do a Y rotation, instead of rotating around itself, it's actually, spinning around the room. Now, if I change this, on the other hand, to okay, ZYX, now Y is before X. So now, if I rotate Y and then X, so X is always going to be leaning forward and backwards, which is what I expect with my finger, with my mouse going up and down, and Y is always going to be rotating, around itself like a top. So Y is not affected by X, but X is affected by Y. And to me, that feels much more natural in terms of the mouse controls for X and Y. So that's what I'm going to do. So my rotation function here then, what I'm going to need to do is the outer call will be the one that's done last, right? So I'm going to then call rotate X, which will be after calling rotate Y, which will be after calling rotate Z. And now rotate Z has the actual point in it, and so rotate Z takes the Z angle, rotate Y takes the Y angle, and rotate X takes the X angle. Okay, and now when we call our rotate Y, we're actually going to change this just to rotate, and we're going to change this to rotation angles, and same here. Okay, and now that's now set up correctly. So all we have to do now is handle the dx and dy, and here I need to change this to if not mouse down return. This one should actually be mouse up. And basically, as I said before, so dx is going to be affecting our y rotation, and dy is going to be affecting our x rotation. So rotation angles dot x plus equals dy, and rotation angles dot y plus equals dx. And since that's probably going to be far too much, we're going to multiply that by like some const mouse rotation speed. And I will just define this somewhere at the top. For consistency, I will make it uppercase. Okay. And let's try that out. Let's get my penger. And okay, it seems like it's working, but it's actually going the opposite direction than the one I expect. So let's just go back here and actually subtract the dy and the dx. And one more thing that I want to do is I want to stop the automatic rotation when the mouse is down. So I'm just going to say here, if not mouse is down, then I'm going to do this. Okay. So now if I get my penger, yep, that's working perfectly now. Okay, so there we have it. That's the Canvas OBJ wireframe renderer. So we can import any arbitrary OBJ file. We can use our mouse to rotate it. We can flip the handedness if need be. And again, it's only 227 odd lines of code. So hope you have fun with that, and take it even further. I'm gonna clean this up a little bit and then post it on GitHub and add the link below. And if you haven't already checked it out, you should check out Zozin's original video, and it'll make this make much more sense. So thanks.